Hey everyone, today we're going to work on day 2 of our integrals and net change, and we're just going to be looking at 3 AP questions. So these are actual questions from old AP exams. And so really we want to go through, make sure we understand how to work with these rate functions, and get an idea of the kinds of questions we can be asked when we're dealing with these rate functions. So the first one from the 1999 exam says the rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r. So here again we have a rate, so that's going to be important. The table to the right shows the rate as measured every 3 hours for a 24-hour time period. So for part A, we're going to use a midpoint Riemann sum. We want 4 subdivisions of equal length to approximate the value of the integral. And then using correct units, we're going to explain the meaning of our answer. So let's go ahead and do our Riemann sum. So if I want 4 subdivisions of equal length, I know I'm going to have subintervals that are going to be 6 units long. So I'm going to set that up first. Okay, and I know I'm doing a midpoint approximation. And so I'm going to grab my values from the table. So between 0 and 6, I'm going to grab the value at 3, which is 10.4. We'll look at 9 as 11.2. 15 is 11.3. And then 21, we've got a value of 10.2. So now I have equal subintervals. So I can just do a base of 6 for each of my rectangles, and I'm going to add the heights. And then I'm going to grab my calculator to get the value of this integral. Okay, and so I get 258.6. And let's see, I was multiplying gallons per hour times hours, so I know my units are going to be gallons. So I know that the integral from 0 to 24 of r of t dt is approximately 258.6 gallons. Now, in terms of the problem, right, what that means is approximately approximately 258.6 gallons of water flowed out of the pipe over the time period from t equals 0 to t equals 24 hours. Oops, sorry, that kind of ran off the page there. So when we find that answer, that's just telling us the amount of water in gallons that flowed out of the pipe over that time period. And again, we need to be careful to mention our units. So I mentioned the units for water and then the units for that time period. Okay, so then for part B, it says the water flows out of the pipe and into a water tank that originally contained 115 gallons of water. So we're getting an initial value here. So if the total capacity of the tank is 350 gallons, will the tank be able to store all the water over the 24-hour period? So let's see. We know that the amount in the tank is going to be equal to our initial amount plus the water that flows in. So plus the amount that flows in, right? Or our net change. So for our problem, we know our initial amount is 115. We know the amount flowing in is given to us by that integral. So from 0 to 24 of r of t dt. Oh my goodness, I just realized you can't see any of what I just wrote. Sorry about that. Okay, so here we are. So the amount of the tank was the initial amount plus the amount flowing in. So our initial amount was 115. That net change is given to us by integrating the rate function. Well, we know that the value, let's see, approximates this rate we just found, right? We know that's approximately 258.6. So if I add those two values, I'm going to get 373.6. Since that amount is greater than the capacity of the tank, we know that tank won't be able to store all of the water. So we can say here, since 373.6 is greater than 350 gallons, the tank will not be able to store all of the water. And I'm going to specify over the 24-hour period. Okay, so that's our first problem. So now we can see with these net change and rate functions, they can ask us to calculate Riemann sums. And again, this is a more standard, keeping in mind that the amount is going to be equal to our initial value plus our net change. So let's go ahead and look at the next problem. Okay, this one we've kind of seen before, though we really hadn't tackled the whole FRQ. So we have our amusement park problem, and we're given the rate at which people enter the park, and then we're also given the rate at which people leave the park. Okay, now we know the functions are valid for 9 to 23, so those are the hours of operation. And we know that at time t equals 9, there are no people in the park. So our initial value at t equals 9 is 0. And so that'll be important later on. So for part A, it wants to know how many people have entered the park by 5 o'clock p.m. And it wants us to round our answer to the whole number. So to get the amount of people who have entered the park, we need to integrate the rate at which people are entering. So I'm going to integrate. Let's see, I want to know by 5 o'clock p.m., so I'm going to integrate from 9 to 17, and I'm integrating e of t dt. Again, to integrate the rate function is going to give us that change. So now I'm going to use my calculator to calculate this. So I'll go Math 9. Sorry, this is a bit dark here. I'll try the light. Oh, let's see if that fixes it. Okay, can see the calculator a little bit better now. So we're going to integrate from 9 to 17. And then we're going to do our function e of t. So I have to be careful here. So I'm going to do 15,600 divided by, I'm going to use parentheses. So x squared minus 24x plus 160. Close my parentheses, and that's with respect to x. And so we get approximately 6,004. So let's see, 0.270. So that value is 6,004.270. And so then we know approximately 6,004 people have entered the park by 5 p.m. Okay, so there's part A. Okay, now Part B has to do with the price of admission and how much money they're collecting from people entering the park. So we know the price of admission is $15 until 5 p.m. And then after 5 p.m., the price of admission is going to go down to $11. So how many dollars are collected on the given day? And we're going to round to the whole number. So now I know that the amount of money collected has to do with the people entering the park. So I'm still going to be integrating E of t, because that tells me how many people are entering the park over a given time period. So now I know I collect $15 from 9 to t equals 17. And then I'm going to collect $11 for anyone entering from, let's see, 17, and then we close. Our upper limit is 23. And again, that has to do with people entering the park. So again, we'll go back to our calculator. So I've got two integrals now. So 9 to 17. Being careful about how I enter this function. And then I'm going to add 11 times, did I multiply that by 15? Nope, I did not. I need to go back and multiply this. So insert. There we go. So now I've got 15 times the integral plus 11 times the integral from 17 to 23 of the same function. And that's with respect to x. So let's see, 104,048.165. So approximately, we want it to the whole dollar. So we have approximately $104,048 are collected from admissions. Okay. So on to Part C. So C is giving us another function. It's defining h of t as the integral from 9 to t of e of x minus L of x dx. Okay, so we're going to find, it's actually telling us the value of h of 17 is 3,725. So we have to find the value of h prime of 17, explain the meaning of h of 17 and h prime of 17 in the context of the amusement park. So first of all, let's think about h of 17. Okay, so now I know if I integrate the rate, that's giving me the net change. So here I'm getting, if I integrate this, I'm getting the amount of people who entered minus the amount of people who left. So what that's telling me is that at h, so at t equals 17, it's giving me the number of people in the park at time 17. Right? And so what they're telling us is, by telling us h of 17 is 3,725, they're telling us that there's 3,725 people in the park at time t equals 17. So for the meaning, we're going to say that 3,725 people were in the park at t equals 17. All right, so now let's think about h prime of t. So I know h prime of t is going to be the derivative of my integral . Well, again, we know derivative of the integral. Again, that's just our very familiar by now fundamental theorem. So all I'm going to do, since my lower limit is a constant, my upper limit is t, I'm going to go ahead and replace my x's with t. So h prime of t is just e of t minus L of t. So now, if I'm talking about h prime of t, it's just the difference between the rate that people are entering and the rate that people are leaving. So it's going to tell me how that rate of people entering the park is changing. So let's go ahead and calculate h prime of 17. We know that's just e of 17 minus L of 17. So if we calculate that now, we're not integrating anymore. We're just finding those function values. So I have 15,600 divided by 17 squared minus 24 times 17 plus 160. And I'm subtracting L of t. So now I have to use my second function, L. So 9,890 divided by 17 squared minus 38 times 17 plus 370. All right, and so I get negative 380.281. Okay, so now I have to explain the meaning of that, right? What that is telling me is that the number of people in the park is decreasing at a rate of 380 people per hour at time t equals 17. So this is telling me about the rate at which people are in the park. So the rate, or excuse me, the number of people in the park was decreasing at a rate of approximately, I know I'm getting down to the bottom here, so sorry about that. Number of people in the park was decreasing at a rate of approximately 380 people per hour at time t equals 17. So more people were leaving the park than were entering. Or they're leaving at a greater rate than they were entering. Okay, now last part, and I'm going to kind of cover this up and just go onto a separate sheet of paper here. So pause if you need to get any of those notes. Okay, so for part B now, or D, excuse me, at what time does the model predict that the number of people in the park is a maximum? Well, we said before, we know that h of t represents the number of people in the park. So if I want to know where that's a maximum, I know I need to take that derivative, h prime of t, which we now know is e of t minus L of t, right? We found that by using the fundamental theorem. I need to take that derivative and set it equal to 0. And if I can do that, then I can get the time when the number of people in the park is a maximum. So again, we're going to go back to our calculator to calculate that. So here I'm going to go to my y equals, and I'm going to type in my two functions, and then, so I'm going to do e of t minus L of t, and then we'll see where that's equal to 0. And then minus my second function. And again, I highly recommend that you're doing this on your own calculator with me so you can make sure that you're getting your parentheses right and all your formatting's okay. So we'll go ahead and graph it. I'm going to have to change my window. And I'm going to change my x values between 9 and 23 since I know that's my domain for this function. So I'll go to Window, change x from 9 to 23, and we'll see where we cross the x-axis here. All right, so there we go. So calc, I'm going to find a 0. So I want to get where I'm above the x-axis. Let's see. Okay, so I've got positive y here at 15.7, so I'm going to use that for my left bound. I'm going to go until I see I have a negative value here, hit enter again, and so here's my time at 15.795. Okay, so I know t is approximately 15.795. Okay, so the model predicts that the number of people in the park is a maximum at t equals 15.795. All right. So we've got one more question to go. Again, I know this is a long video, but hang in there. All right, and we'll do number 10 from the 2003 exam. All right, so now you can see we're not given functions, we're given a graph as well as a table. So a different way that this information can be presented. So we have the rate of fuel consumption. Again, consistent here, our function is a rate function. So in gallons per minute, recorded during an airplane flight is given by this function. So differentiable and strictly increasing. That'll be important later. Function of r, or function r of time t. Okay, so I have the graph and a table of values over the interval from 0 to 90 minutes. Okay, so for part A, it wants us to use the data from the table to find an approximation for r prime of 45. Right, so we know r prime of 45 would be the instantaneous rate of change. Okay, now to approximate that, what we're going to do is we're going to use the slope. Since we don't know that exact value, we're just going to use the slope. So using the table, I know that r prime of 45, well, I want to pick values that are close to 45, so I'm going to choose 50 and 40. So I know this is going to be r of 50 minus r of 40 over 50 minus 40. So let's see, we have 55 minus 40 over 10. So 15 over 10, or 1.5. Now we have to be careful with our units here. My numerator was gallons per minute, and my denominator is minutes, so my units are going to be gallons per minute squared. So that's going to be the average rate of change. Okay, part B wants us to approximate the value of this integral using a left Riemann sum. Okay, so a left Riemann sum with 5 subintervals indicated by the data in the table. So we're going to set it up, and I know you can't see the table on the video, but you can look on your sheet. So I have from 0 to 30, 30 to 40, 40 to 50, 50 to 70, and 70 to 90. And again, we said this was a left sum, so I'm taking those left values. So I'm going to have 20, 30, 40, 55, and 65. So now I just have to be careful. I don't have equal subintervals, so I can't factor out a common base. So I'm just going to do 30 times 20 plus 10 times 30 plus 10 times 40 plus 20 times 55 plus 20 times 65. And so quickly adding those up. It's going to give me 3,700. And again, I'm multiplying gallons per minute times minutes, so my units are going to be in gallons. Okay, now it asks me to explain the meaning of that integral in terms of fuel consumption for the airplane. So we would say the integral from 0 to 90 of r of t dt represents, let's see, this was rate of fuel consumption. So the total fuel consumed by the airplane measured in gallons. We need to specify our units. And then we would say over the time period from t equals 0 to t equals 90 minutes. Let's see, did I get cut off there? Yep. All right. Okay, so now for part C, we need to know if our approximation is an overestimate or an underestimate. So now, here might be helpful to look at the graph. We know that our function is strictly increasing. That's where I said this would come in handy later. So if I just kind of sketch in some rectangles, if I'm doing a left Riemann sum, if I sketch in some rectangles here, I can see that doing this left Riemann sum is going to give me an underestimate because I am underestimating the area under that curve. So for part C, I can say the approximation is an underestimate because, and here's where we have to specify, because r is a strictly increasing function. So it has to do with the fact that r is increasing. All right, and part D I'm actually going to leave off for now. This is a concept that we'll get to a little bit later in this chapter, so we'll revisit it at that point. So that's it for today. I know that was probably more than enough. And again, when you come back tomorrow, we'll get lots of practice working through these problems. Thanks for hanging in there.